what I wanted to start with today is sort of a little elemental thought problem, math problem we're going to do. And I think it'll point to something in your intuition that's always messed up. Okay? So it'll teach you when to trust your intuition and when not to trust your intuition. So here is x, and here is y. Okay? That is not a kinematics plot. That is a real space plot. It's actually everything's in the right direction because we're going to consider gravity down like this. So that is literally like the plane of the board. Okay? And I'm going to take this obnoxious piece of chalk right here, and I'm going to use my hand, and I'm going to move it from one position to another position at constant velocity. Are you ready? This is very exciting. Hold on. You ready? Just like that. Pretty cool. Yes. Hold your applause, please. I'll do it again. From A to B at constant velocity. Or you can think of it this way. It's constant velocity, so let's have it move the whole time. You didn't see how it started moving. You don't care how it started moving. The problem is about moving it at constant velocity. It's always been at constant velocity, and we care about A to B. Okay? So let's draw that real quick. So here is the chalk at A, and here is the chalk at B. And we're talking about the displacement from A to B like that. Okay? That's it. That's all we're going to talk about, A to B. So what we want to say is we went from A to B at constant velocity. So the problem would lay that out more explicitly with lots of words and commas and punctuation. So we want to know is what is the work by my hand from A to B? So that would be the question. That would be the problem. Okay? Doesn't sound too bad. You say, okay, work was a force you apply times a displacement. That's what that R is. So you'd say, well, first let's just get R. The work equals FD, force times distance. What is D? What is R? Whatever you want to call it. R, S, X, Y, whatever you want to call it. In this case, since we're in a two-dimensional system, it's good to call it R. Because we're not just going in X, and we're not just going in Y. So in physics, we often use R. Right? So the vector is kind of like this line I drew between them already. Right? So there's R. We displaced like that. Okay? Now to do work, or to calculate work, the work by my hand, we need the force that my hand applied. Right? We need the force of the hand. And this is the weird intuitive part of this problem, is what force is my hand applying to get from A to B? All right, so I think to start, why don't you draw yourself, draw the force on your notes. I'll give you 15 seconds to think about it. If you had to draw the force vector of my hand on that mass, what would it look like? 15 seconds while I read these. Why are A and B? Oh, A and B are not vectors, they're points. Did I put vectors? Oh my God, I don't know what that was. I'm just feeling overly decorative today. So those are just points, A and B. They could be vectors from the origin. They are positions, but we won't get into nitpicks. Yeah, they're just points. So think about what that force looks like. Okay, so hopefully you drew an arrow. I think all of us are at that point. Hopefully we all drew the force as an arrow with an arrowhead on it and labeled it with an F. But now let's think, which way is it? So what you want to do is your intuition might say, well, it's along here, right? Something is moving along there, therefore I must be pushing it along there. And that's why this is an interesting intuition problem. It's not this way. Let's give it away. The force is this way. Yes. If you got that the force is straight up, you can trust your intuition. And when you're taking the exam, trust your intuition. If you thought that the force was this way, don't trust your intuition all the time. It's okay. Probably 90% of you said the force is this way. Okay, but when it comes to forces like this, that's the deal. My microphone is off. Okay, so yes, I was insulting your intuition, right? If you thought the force is this way, don't trust your intuition, or your intuition needs to develop more. Okay? But let's think about what to do. What if you don't trust your intuition? What do you do if you're unsure? Okay, so first let's think, what do? You write the forces out, right? If you're ever sitting on a problem and you just don't know what to do, I'm just going to have to shout, and you don't know what to do, in this entire semester, apply Newton's second law to everything in the problem. Okay, that's the backup. That's like DEFCON 5. I don't know what to do. Just start writing this. Sum of the forces equals ma. You'll at least get partial credit. Okay, but that is actually the key. That's the key to solving every problem in this class. Technically, you could solve anything with this. So in this case, you might say, I don't know which way the force is. Let's write sum of the forces in the x equals ma in the x. and sum of the forces in the y equals ma in the y, right? Now, we're at, let's do x. We're at constant velocity. If we're at constant velocity, we're at constant velocity in both directions. Vx is constant, Vy is constant. They're both constant. So the accelerations are both 0. Right? So this is a case where that's 0 and that's 0. They're both 0. OK, so they're both 0. So now let's think, what are all the forces in the x? I mean, I guess we're trying to figure out F push, so I'll write it down. F push in the x, and there's no other ones. Therefore, what does F push in the x have to be? It's 0. Newton's second law wrote it down for you, right? All you gotta do is put like a box around it now, full credit, okay? So there's no x component to F push on the piece of chalk because it's moving in the x and there's no force pushing it back, right? What about the y? Well, we don't know. We're trying to figure out F push in the y. Are there any other forces in the y? There's the weight. Minus mg down. We have to counteract the weight. Okay? So you find that, oh yeah, the force of the push in the y equals mg, except up. I mean, this is with components, right? So basically you have a force up, and its magnitude equals mg. Okay? So think about that, right? Motion at constant velocity means the net force is 0. So for the net force to be 0 in x, we don't have to push it in the x. For the net force to be 0 in the y, we have to push it in the y. Okay? That's what I was doing. So it's going that way, and I wasn't even pushing it that way because of Newton's first law. I said it's already going that way. Why would I need to push it if nothing is pushing back? All right. So that's the weird intuition part about this problem. Before we move to the actual solving it, here's an excellent question. This is really annoying. Aren't you applying an x component that is canceled out by the friction between the chalk and your hand? Good question, right? So if that confused you, stop listening for a minute. Let me turn this back on. But let's just think for a second. Technically, I'm talking about the external force that's pushing the thing up, right? There is also, technically, as I'm moving it, oh no, there is no friction force. You're wrong. Never mind. You're throwing me off. There's no friction because there's no need for there to be a friction. Remember, the static friction is 0 up to mu s times the normal force. In this case, it's 0. It's whatever it needs to be, and we don't need one. Why did I reveal my ignorance in front of so many people? I prefer more people. Okay, so that was intended to help, except for all the mic trouble and all the confusion. Everybody looked like massively confused. I've never seen this many confused faces in my life. So this was a complete failure. The F push is straight up. Let me just do you the normal physics teaching way. F push is straight up, obviously. Okay, let's do the problem now. Okay. So F hand is like that, mg. Okay? Straight up, the magnitude mg.